This video will help you with your Chapter 6 Circular Motion assignment on Mastering Physics. So the first question talks about a pickup truck driving around a curve on flat road, we assume. And in the back of the pickup is a steel toolbox that is obviously resting on the steel bed of the truck, where coefficient of static friction is 0.82. And the question is, just how fast can you go before the steel bed and the steel toolbox then begin to slide relative to each other? So we'll look down on the truck with this box in it, and we'll assume it's turning around a corner this way. So we're looking down here, the wheels of this truck. Now, if there weren't static friction to help you turn the corner, then you would just go in a straight line, as would the box on the bed of the truck. So the forces acting are, the normal is straight up towards you, the force of gravity is straight down towards you, and they balance each other. Okay, the thing that is causing the truck to go around the corner is the force of friction. And that is static friction. So you turn the wheels, it pushes against the road pushes back against the wheels, and that's what makes you turn the corner. And similarly, between the steel box and the truck is also the force of friction, making it turn a corner. Okay, so let's just worry about the box for now. It's circular motion, and so uniform circular motion, which means the speed stays the same. We have the force in toward the center of the circle equal minus the forces out. There are no forces out here. This equals mv squared over r. Okay, so this net force in, which also gets the fancy name centripetal force, but I don't like to use that term. The net force in is just the force of friction, is mv squared over r. So that's the equation for any vehicle driving on a flat road, turning a corner, or going around in a circle. Now we know the force of friction is equal to mu Fn, and we also know that Fn is mg as long as it's a flat horizontal road, not banked. So this would be mu Fg, and so then that's mu mg. So if you put that into this equation, you get that the force of friction, mu mg, is equal to mv squared over r. And notice how it doesn't matter what the mass of, whether it's the car or the steel box or anything going in this circle at this speed, it cancels out. And so we have that mu g is v squared over r. Now, when you have problems like this, there are three variables. There's the coefficient of, and that's static friction, the speed, and the radius of the curve. So you could be told any two and be asked for the third. So in this case, we're told the coefficient and we're told the radius, and we're asked for the speed. Okay, so we solve for speed. V squared would be mu times g times r. And so v would be the square root of mu g r. So it's the square root of 0.82 times 9.8 per kilogram times, and r here I think is 21 meters. That's times 21. And when you do that, you get that the speed, the maximum speed before slippage occurs, would be 13 meters per second. After that, things would start to slide, whether it's the tires on the road or depends what the coefficient of friction is between the tires and the road, but for the steel box and the steel bed of the truck, that would be the maximum speed before you start to slip. For slipping. Okay, question 2 deals with a Ferris wheel. It's a classic question. And remember, it's all about the forces in and out of the circle. So with a Ferris wheel, you remain upright. You don't go upside down like you do in a roller coaster. So here you are on this Ferris wheel. But whether you're on the top or the bottom, it makes a difference, because although the force of gravity is always down, if you're on the top of the circular path, force of gravity is an in force. If you're on the bottom of the circular path, the force of gravity is an out force. And remember, Newton's second law for circular motion is in minus out equals mv squared over r. So it makes a huge difference whether you're at the top or the bottom. Now, they talk about here apparent weight. Remember, apparent weight is the normal force. It's the force, if you were sitting on a bathroom scale, it's the force the scale would have to push on you in order to keep you from falling through the scale. So apparent weight is always the normal force. True weight, I think they call it in your book. True weight, yeah, they call it true weight. That never changes, that's Fg. Okay, so the two forces acting on you, whether at the top or the bottom, are Fn and Fg. So Fn is up when you're at the top. It's always up. But it becomes the in-out are different. Okay, so where are we analyzing? Are we analyzing at the top or the bottom? So it says here we are at the top of the ride. Okay, so we're doing this top of ride. Okay, so in would be Fg and out would be Fn. And this would be mv squared over r. Okay, so if we solve this for Fn, our apparent weight, we get Fg minus mv squared over r. Now I can write this as mg minus mv squared over r. And so I can factor out the m, because notice how we're not told m. We're going to have to do something about this m. Now, if you're not told m, you can always make up any number you want. Use 1 kilogram, because it's the same whether you, whatever your mass is. So if it bothers you to do the algebra here and factor out this m, just let m be 1 kilogram. Okay, so that's Fn. And we're going to want the ratio of apparent weight to true weight. Apparent weight to true weight. And so that would be Fn divided by Fg. And so we use that Fn up there, mg minus v squared over r divided by mg. And notice how the m's cancel. So even if you put in 1 kilogram, it wouldn't have mattered, or 2 or 10 or 60. Okay, so this ratio that they're talking about would be g minus v squared over r. Remember, v squared over r is your centripetal acceleration. So it's, this number is less than 1 because the top is smaller than the bottom, and it's less than 1 by this ratio of the centripetal acceleration to g. So you could actually write this as 1 minus v squared over rg. If you wanted to, you don't have to go that far. But so this is smaller. Now, if you did it the other way around, if you did it at the bottom, you would find out this is positive, and then it would be bigger at the bottom because you feel heavier when you go around the bottom. Okay, so that'll be, we'll use that. But first we need to find v. So part A to this question is, what is the speed? So we're given that r, the radius of the curve, is 19 meters. And we're given the time to go around once. That gets a fancy name. That's called the period of motion. To go around equals 25 seconds. Now, to get your speed, remember it's uniform speed, same speed the whole time. Speed is equal to distance divided by time. And so the distance once around is 2 pi r, circumference of a circle. The time to go around is 25 seconds. And so this is how you get your speed. 2 pi times 19 meters over 25 seconds. Turns out that the speed is equal to 4.8 meters per second. Okay, so that was A. B is, what is the magnitude of your acceleration? Acceleration. Now, even if you're going at the same speed, the acceleration is from the changing velocity vector direction. So A is v squared over r. Just put this 4.8, square it, and divide by 19 meters. And you would get 1.2 meters per second squared. Okay, and then C, the ratio, we already worked that out, was G minus, now I can remember it was V squared over R, so that's A, all divided by G. So it's 9.8 meters per second squared I'll use here, minus 1.2 over 9.8. And that ratio, less than 1 as we expected, is 0.88. Okay, so there's a couple of good circular motion questions.